Well, you want me to get a glass of champagne?
Well, I'll relate some of our stories when we get going. So let me make an introduction. Are you ready?
I'm, I'm ready to be introduced. Always.
Okay. So my name is Jeff Baer. I'm with Almaz Capital. And prior to Almaz, I was the CTO for networking at Sun Microsystems. And one of the people I was fortunate to be able to convince with much arm twisting to come and work with us at Sun many years ago was Dr. Whitfield Diffie. And Whit, in addition to being a good friend of mine, a connoisseur of very good sushi and sakes, and also an altogether good bon vivant, happens to be one of the world's experts in cryptography. But the reason we asked Whit to speak to you was not to give you a technical lecture about algorithms, because you can all go back to school and be bored by the same professors who bored you initially, and we didn't need that. What we wanted was somebody who is a world-class cryptographer, who has experience worldwide with public policy, who knows the state of cryptography, the lack or the gain in progress, to talk both about where the opportunities are, where the deficiencies lie, but also to have a perspective from what we call the 10,000 meter view of what's really going on out there. What are governments opposed to? What are they pushing? But we're not going to ask Whit to tell us what the answer is, as opposed to an opinion. So Whit, after you give a talk,
I think I'll go away. What, you're not going to accept my answer? This is ridiculous. Why do I waste my time?
So I will be sitting on stage. After you give a talk, I will kind of throw questions at you from the crowd, and there might be a moment delay while they are translated. But let's go give the talk portion first. So with that, I give you, well, let me make one other sense. You've heard of Diffie-Hellman, you've heard of public key cryptography and these things. Well, the person who invented it is sitting here. And the very last thing I will say before I do hand it over is he invented it in the shower and he forgot. So he walked out of the shower and wrote in water on the wall the initial algorithms, then went back in the shower. So now I have told the embarrassing story about him. I will let him try to make up for that. So with that, Dr. Whit Diffie.
Thank you very much, Jeff. So I'm sorry, I'm a stickler for detail. And no, I was sitting in the living room at John McCarthy's old house years ago at Stanford University. And then I had this idea, and then I was thirsty. So I thought I'd go down to the kitchen and get a Coke. About halfway down the stairs, I thought, oh, I was thinking about something interesting. What was it? I can't remember what it was. Fortunately, I remembered it. And as I like to say, I've been making a living off of it ever since. So whenever I try to think about these great world problems that Jeff is asking me to talk about, I remember years ago, I was living in Berkeley, and I picked up a political leaflet that had a wonderful analysis of what was wrong with everything. It said, the left wing and the right wing, or the left wing and the right wing of the same old bird. And I think you can see it's not flying too well. And everything I have time, I think about internet security or anything, essentially anything else, this comes back to my mind, and sort of every approach we've tried is busy fighting for itself, and that doesn't mean they solve the problems. Jeff, something's still coming in as a whole bunch of squeaking and rattling. I guess if it doesn't bother the audience, I can put up with it.
Okay. Is that any better, Whit?
Probably.
Okay, let me ask them to turn off the other microphones. Except
Got a
for
real
number two.
homey.
Okay, if you can carry on. We have some folks standing by. Okay, so if you carry on, we'll carry on.
Okay, very good. No, it seems fine now. So we're sort of in a paradoxical situation because network security kind of arose out of communication security, which was mostly cryptography. And for some reason or other, cryptography is doing misleadingly well, whereas network security is doing dreadfully. I mean, basically, at the time of World War II, everybody was justifiably nervous about cryptographic systems. World War II, after World War II, all sorts of major systems were broken. It was a very important feature of certainly the intelligence aspects of World War II. But if you look at cryptography since then, the lifetimes of cryptographic systems in serious use have been quite long. I apologize, I don't know the Soviet, the Russian, the Warsaw Pact systems as well, but in NATO, systems have gone into service in the 50s, been taken out of service in the 80s. The direct failure of the cryptography is not currently the problem. And at the same time, if you go from starting with cryptographic algorithms, which are doing fine, to cryptographic implementations, to platforms that they run on, to applications, the security of everything else is just dreadful. And the question is, can we figure out why? And even if we can figure out why, can we do anything about it? Well, and part of this paradox is that even up through nuclear weapons, you had a sort of a conservation of energy rule in security, which meant that the cost of defense was, loosely speaking, proportional to the cost of offense. So return to World War II, naval ordnance, you had an approximate relationship between the size of naval artillery and the thickness of naval armor. The trouble is, in all of the information stuff, it's not vaguely clear. So in one sense, it appears possible for a reasonable size organization to develop cryptographic systems that might plausibly stand against all the world's efforts for years. On the other hand, and that one we have pretty good reason to believe, and there's no logical reason it shouldn't be true of more general computer network security systems. But on the other hand, it's not obvious that a small group of people, also modestly funded, can't develop network penetrations that will bring down the whole internet. And we've seen some things with substantial impact, and exactly how these things respond to investment is not terribly clear. On one hand, the one thing one can really see where investment helps is that if you're developing penetration, it is very valuable to have the techniques and the resources to run your malware, in particular in captive networks. So you look at the first internet worm in the late 1980s, what was wrong, the reason that worm got out, is that Robert Morris the Younger didn't have a genuine captive network. He was running on the network in the computer science department at Cornell, and he couldn't keep control of this thing that he developed. I was working at the time for the laboratory of the Canadian telephone system, and we really knew about running things in captive networks, and I thought to myself, we wouldn't have had the imagination to develop this thing, but if we had, we would never have made that mistake. And heaven knows what people who do have our resources and hostile intention might do in development of malware. And 25 years has shown us that it's a growth industry. So what else can we figure out about this problem? I mean, is this problem really so difficult we can't solve it, or is there something else wrong? And I think there are some issues of difficulty, and I'll get back to those. But let me start with a couple of observations from people I think really put their fingers on aspects of it. At the RSA conference in San Francisco this year, we had on the cryptographers panel a man named Ed Giorgio, who is hired of NSA and who billed himself as having been both the head of cryptography and the head of cryptanalysis at different times. And he said a great thing. Not sure it's true exactly as he said it, but I think it has a large grain of truth in it. He said, cryptography is more important. Cryptanalysis is more fun. Then he went on to say when he was head of cryptanalysis, he had 100 times as many people working for him as when he was head of cryptography. That doesn't sound like more fun to me, but each to his own. Suppose you generalize that a little bit and say that development of defense is more important and development of offense is more fun. I think that actually fairly well describes a lot of what's going on in the current world, because we genuinely need network security as part of the platform on which we are building modern society. And make no mistake about this, we're doing something hasn't been done in 5,000 or 7,000 years. In that era, we began to move into cities. For the first time, people began to live less in nature and more in an environment created by people. So what had been, in many cases, a natural fact of life now became a function of civic policy. So all of the things we are dealing with today should be seen in that light, that we are dealing with a set of policy decisions, and they don't all come in that form, right? I mean, starting up a company is effectively a policy decision. Adopting a technology, writing a piece of code, all of these things become part of the fabric of the world and determine who is going to be more powerful, who is going to be less powerful in the world of the future. And so nobody's going to let these issues rest. Too much rests on it. And the reason the things we called in the US the crypto wars, arguments over people's right to use cryptography, et cetera, are not going to go away, is that they are really fundamentally important to who's going to prosper and who's going to wither. So come back to security is more important, attack is more fun, and that explains part of it, but another aspect of it is, well, what about the funding? And my next quote comes from a man named Bruce Held, who is the head of, he is or was when he said this, the head of counterintelligence at the US Sandia National Laboratories. That's the Nuclear Command and Control Laboratory. It's planning to get you. Bruce Held said, yeah, you're doing defensive work, and you go to your boss and you say, I need 1 million rubles to defend the labs next year. Your boss says, you know, we're kind of tight on funds. What could you do with 800,000? It's seen as a cost center. It's seen as a cost that you would like to reduce. It's seen as something you'd like to avoid. You're doing offensive work, what they call network operations. You go to your boss, you say, I need 1 million rubles to do this work next year. Your boss says, well, you know, we like the results you've been getting. We like the information you've been getting for us. What could you do if you had 1.2? Now, that really rings true to me more than many of the explanations these things have been given. But it goes hand in hand with something else, which is kind of along the lines of the offense is more fun, which is that we have a tradition that dates back into the Cold War of notions of deterrence and retaliation. We want to fight, or we want to be planning to fight. And so we think about network, how do we keep somebody from breaking into our network? Well, one possibility is that we make the network strong enough they can't do it. And very frequently, if you say that, people talk about the failure of the French Maginot Line, which was incidentally fundamentally political. It's not that where they built it, it wasn't strong enough. It's that they didn't build it on the Belgian border because Belgium was an ally and may not have seemed necessary and it would have offended the Belgians. But what you choose to do for what reasons is very important in this. So a lot of people grew up in the Cold War where we had this notion of deterrence. And we had it not because it was a great idea, but because we had no better ideas. And these same people are now thinking about cyber policy, talking about cyber weapons as the new nuclear weapons, et cetera. And they're thinking in much the same terms about deterrence and have given up, I think, prematurely on more purely defensive functions. And I'll come back to that. So I would say that we've developed a sort of a codependent ecosystem with the malware. There's a whole lot of money being spent on security, and it's being spent, so to speak, if you can say offense is fun, security is more important, well, maybe you can divide security into two pieces. You can say, well, the more interactive part of security is more fun. And, 20-ish years ago, this sort of was a revolution in thinking in network security. And old guard like me, who believed, to paraphrase it, in building stronger crypto systems or basically introducing purely defensive sort of barrier methods of protecting networks, it came to be the common wisdom that that wouldn't work and that we needed a more interactive system, that the barriers would slow people down and we would see where they were slowed down, we would counterattack and so forth, kind of the way a castle worked with its garrison. The castle by itself, was not something one or two people could live in and nobody could possibly get in, but with a garrison of several hundred people, then it was a big asset in defending itself. Now, so what I'm going to argue, what I do argue, is that if we were spending as much money on actual defense as we are spending on the current sort of interactive attack and defense system, we might actually get much better results. Now, that isn't necessarily easy to try, right? Because the problem is the way these things work, something that can get funded, something that has a chance of making money, is typically a point solution of some kind or other. So people are being plagued by viruses. We say, well, we will develop a better virus filter in one sense or another. Either it will at some level study the activities of viruses. It will more and more dynamically develop mechanisms for detecting the viruses. It will keep them out, and that will solve your virus problem. Oh, now about your spam, well, we have another product over here to solve that. And so we've seen a whole companies all over the world arise developing things that solve some part of the problem, not seemingly terribly adequately, but that are eating up resources that might in principle, perhaps in something like a planned economy, be spent by the major system developers to develop fundamentally more secure systems. Now, side by side with that is the fact that I think, and maybe this is the single most important thing, is that a wide range of people don't really want you to be secure. Oh, they want you to have certain sorts of security, but in particular, they don't want you to be secure against them. And there is a whole lot of fuss about the fact that, you know, FAPSI and NSA might think that. And NSA has been very public in lobbying in favor of having some kind of access mechanism so that private individuals can't have real security. They can have security up to a point, but the government can always get into their systems. I think the government's kind of the least of them. I mean, Mike Hayden, one of the former directors of NSA, very strong on this point, and he makes a claim I'm very skeptical of. Says, you know, either you can have the government able to get at your stuff, or you can have other governments able to get at your stuff. I'm not quite sure why he thinks his being able to get at it's going to make it more secure, but that's what he says. But the question is, you know, fact is, almost nobody wants you to be secure. You think Apple or Google or Amazon or any of the major companies want you to be secure against them? On one hand, of course, insofar as their cloud activities and anything other than storage, then at the moment they pretty much have to have access to your information. But even if you're talking about somebody like Apple and Microsoft, who make end user products, what they would like to do for you is manage the updates. Well, if they manage the updates, they manage what control code you run. And it's not clear that even if you guarantee yourself that you never install updates that you don't have evidence was sent to a wide range of people, that you're going to be able to protect yourself against updates that know who you are, know what your computer is, and plan to update your computer in a way that's more helpful to somebody else than it is to you. I had a friend once talking to some of our intelligence associates, colleague once, said to somebody, you know, I don't remember exactly what systems he was citing, but he was saying he was expressing pessimism about, you know, being able to get into these systems, and the other person said, what do you think updates are for? So I've been thinking about what updates are for ever since. So what one just ask yourself is, what would it mean for your computer to be secure? What would it mean to you? And I think the fact is you're actually in an antagonistic relationship with your suppliers the people who make your computers about that subject. Because the first thing you'd probably like is stability, right? You'd like to decide what version of the app you liked, be able to keep whatever features of it you liked for however long you liked. And you might be able to might want to be able to get some new ones when you wanted them. But you wouldn't want them to be changing the way it worked on you from one version to the next, perhaps without your control. One of those things is a very sharp point of contention, right? I mean, I would think you might reasonably say, well, one thing you'd want is you'd want to be able to record whatever you wanted that came to your own computer. But you turn around to the other side of the aisle, and there are these people who want to sort of rent you content. They don't really want you to have control of it. Can you say that's insecurity on your part? I think you can. You need this. You want to have continuing access to it. They say, no, you can have access to it as long as we want you to. So the desire of the people, and the very powerful in this world, who make computers, who write software, to control what you do with your computer is very large. So we have, in my view, a problem that on the face of it could be made much better That is to say that if we spent the resources that are being spent in, I think, a variety of the wrong ways, in kind of interactive security, on developing much, much better both security mechanisms in computers and methodologies for building secure systems for corporations. For example, building multiple networks as an isolation measure rather than trying to stick everything on one network because that's so easy to do and so convenient. And part, at least, of the reason we're not doing this is that the major players don't really want them to be that secure. Now, if you look at the consequence of installing a tailored insecurity of this kind, and just in time, I mean, things like this go way back in secure communications practice. It's all ComSec monitoring. You listen to your own forces and try to discover what you can tell what your opponents might be learning about. But that complicates things. And at this moment in computer and network security, basically, we can barely assure ourselves that anything is secure. And if you complicate it by adding something as elaborate as an access mechanism for certain authorized third parties, then at two levels, one at the straight technical level, as they say, that makes it more complicated. We can barely prove the simplest, barely establish for ourselves that the simplest things are secure. Making them more complicated is not the solution. But in another sense, you acquire a very fundamental sort of insecurity because you have no idea with what the policies of the people who have that access mechanism are. So governments, loosely speaking, exist in a community of governments. Companies exist in a community of companies. So if either one of those has access to your information, what they decide to do with it is going to be determined by the norms of their communities. And we've had cases, look like, it has nothing to do with computers. Years ago in Chicago, there was a reasonable enough complaint that Interpol was asking for information about Polish Americans living in Chicago as alleged part of its criminal investigation activities, that in fact was being used by the police in Poland in their concern over the political activities of expatriate Poles. So in a world where if anyone can be called a terrorist, it seems, right? What are people going to do with your information if they have it? And you thereby, take a managerial view of cryptography, go back to my narrow part of the subject. Cryptography kind of bottles things up in a wonderfully satisfactory way. If I encrypted it here, you received it and decrypted it there, nobody else in the world knew the keys, we know that that whole thing is encapsulated. And if neither of us records it, then it's going to die after it happens. We have a secure phone call, we talk to each other, and at the end of the phone call, the keys go away, and nobody else is ever going to be able to have access to that information. That is one of the greatest simplifying assumptions in all cryptographic arguments. If you install third-party access mechanisms, suddenly it opens it up to no end of complexity. You have no idea what's going to happen. Well, having painted a pessimistic view of the fundamentals, everybody always is interested in, well, what things are coming along, what things are coming up, what might change things. And one thing to ask the court is, what are the most important problems to work on? The cryptographers committed the awful sin from a job prospect of solving a very large segment of their problem. So with the exception of a couple of areas I'm going to mention, marketing new cryptographic systems isn't a very isn't a very attractive activity. But something that deserves vastly more work than it gets is usability. So there's kind of an intrinsic problem. I mean, on one hand, you can imagine having something like a laptop and it has whole disk encryption. Now, how secure is that going to be? Well, it may be that after you get through the technicalities of being careful that nothing unencrypted was written on the disk, et cetera, that it might be pretty good. But how long, who knows the keys? What are the keys? What threat are you trying to protect against? Well, suppose you're very paranoid. You say, well, you want to keep the keys in your head. Well, how long you want the keys to be? Well, even if you're not crazy and don't, not too worried about having a 256-bit key, you want to have perhaps a 128-bit key, or at least an 80 or 90-bit key. Now, to remember that, I mean, if you write that down as hex, 128 is 32 characters of hex, and that's an annoyance. It has to be completely random hex. If you write it out in Latin alphabet or Cyrillic alphabet so that you can pronounce it or so it means something, then it blows up to dozens of characters. Maybe it has been made memorable. Maybe you can remember it without any trouble, but it still takes a while to type it in. And that means you can't really practically use it as the password that unlocks your computer every time you set it aside for 5 minutes. So you have to do something that more involves the guts of the computer. Apple seems to be advertising a solution that basically involves a tamper-resistant chip that won't respond to requests very fast. But basically, more has to be done about what you can do to make high-grade security easy to use and secure at the same time. Now, the most prominent thing that's coming up, as though there weren't enough threats to security, the most prominent one that's coming up, the one most people have heard of, the one that gets sort of as much whoop at least as anything, is what's called quantum computing, which is roughly speaking, the physicists are telling us that if we just fund them another 20 years, they will be able to do computing approximately Avogadro's number in parallel. And if that is successful, it's going to destroy all the currently popular public key cryptographic systems, because what something that quantum computers run called Shor's algorithm does well is find cycles. And both Diffie-Hellman and RSA turn on hidden cycle structure. And if you can find cycle lengths in numbers of the range of 2,000 bits, then these systems are going to get to be in a good deal of trouble. Now, interestingly, the US government in NIST and NSA has made a decision to make itself more vulnerable to that. So maybe they know something I don't, maybe they don't believe it's coming. But in moving to elliptic curve crypto systems, which are better because they're, loosely speaking, they use more complicated arithmetic, and that means you can make the numbers smaller. This uses less power, computes more quickly, et cetera. Very attractive sort of thing to do. But because the numbers are smaller, against quantum computing, they are an easier target. And the margin isn't huge. It's factors of 3 or 4 in size. But I don't understand enough about quantum computing or what its costs are going to be or how far it'll be scalable, et cetera. Right now, every now and then there's a news article about how somebody factored the number 15 using quantum techniques. And so we're up to 4 bits. Let's get to 1,000. However, smaller numbers in that case can't be better than large numbers. Now, there's something else with a very similar name that, and fortunately, its name has slightly begun to change. Some people are hawking it under a different name. But the other term was quantum cryptography. And people trying to play on the words and say quantum cryptography will protect us from the problems of quantum computing, which is has some truth to it. It's not zero truth. But quantum cryptography is a bad term in particular because it isn't cryptography. The key aspect of cryptography as a security technique is that it's independent of the channel, whereas quantum cryptography is a totally channel-dependent technique, kind of like spread spectrum. The new term that's being used that I think is much more attractive is quantum key distribution. And let me describe it in a form that I don't know whether anybody knows how to do yet, but it's a really neat idea, which is the central facility, the place that manufactures keys, produces a key pair. And it produces as two little widgets, quantum-enabled widgets, and it ships them, to one goes to one embassy, one goes to another embassy, whatever the right places are. And then at some point, somebody opens one. And up till that moment, the key was not determined. But the moment somebody opens one, it displays the key, or it loads the key into equipment or something like that. And at that very instant, for reasons called quantum entanglement, the Einstein-Podolsky-Rosen paradox, a whole bunch of fancy physics, the other container suddenly has the same key in it, or the complement of the same key, little technicalities. And these techniques won very anti-third-party access and very secure against transit difficulties. Now, as far as I know, nobody knows how to do it exactly that way yet, but people know how to do it over free space, laser and radio communications and fiber communications. And after all, those are sort of the future analog, perhaps, of physical transport. So I am in at least a guarded way, enthusiastic about this transition of this understanding from calling it quantum cryptography to calling it quantum key distribution, and I think that may play an important role. The other thing that gets a certain amount of news is called homomorphic encryption. And this is really very important to see two aspects of this. Homomorphic encryption means the following dream. You have a big computer. I want you to compute something for me, but I don't want anybody else to know what it is. I don't want you to know what it is. So I want to send you a program that's encrypted. You can't understand it. You can't understand what the data in it are, but you can run it. And so you run my encrypted program for me, and after a while you tell me it's done, you send me the bill, I pay your bill, and you send me back the cryptogram. And you couldn't read it, but I can read it. And I read the cryptogram, and I find it's the answer to the problem I wanted you to compute. Now, that's one aspect of the problem. I remain very skeptical that the way I've described that it's going to work. Because I'm suggesting, well, you had this big computer, like, something I didn't have. I couldn't afford a computer that size, but I wanted to rent some computing on it, and that I could afford. Well, for quantum computing, for homomorphic encryption, ever to become so economical that was going to work, as I say, I see no evidence of that yet. On the other hand, there's another kind of problem. It's called private information retrieval. And I apologize for the US-centric character of this description, but I haven't internationalized it. US Department of Homeland Security, thinks there might be terrorists in Las Vegas. Las Vegas, what they'd like to do, they'd like to go to the hotels of Las Vegas and say, hey, we want to see all of your records on all of your customers because we think there are terrorists and we want to run search algorithms and profile terrorists and figure out who the terrorists are. Hotels say, hey, man, what happens in Vegas stays in Vegas. We aren't giving you our hotel rooms. Why don't you give us the search criteria? We'll do the search for you. Oh, no, our search criteria is secret. You can't have our search criteria. And so they're butting heads. They're at an impasse. And the notion of, quote, private information retrieval is that they can be given an encrypted form of the search criteria. They can run it on their database, and they can return something they won't understand, but they can know because it's a small message that only could have a few people's names in or something, that Homeland Security hasn't succeeded in sneaking out their customer database. So for that isn't a matter of getting the computing power. It's a matter of a different kind of restriction of information. I think there's some prospect for that. Let me close by saying I entertain more radical prospects. So far, none of this has worked. We have imagined for years, at least a generation, that networking was somehow going to bring the triumph of populism, that people would get more control over their governments, more control over their lives, that they could tailor, they had more access to information. In some sense, can't exactly say those things haven't happened, but they haven't transformed the world in the way that many of us hoped they were going to. And I think that doesn't mean that they're not going to. A lot of things take time to soak into society. That if you look at something, you look at a second generation phenomenon like Facebook, right? You see something where it's not so much the technical characteristics that couldn't have been done a few years earlier. It is the social, the fact that there were so many people living in the computer-mediated society that made this possible. So I think all sorts of things that we don't anticipate are going to happen in terms of new organizational structures, new forms of governance made possible by computer networking. And let me just take a simple example, which is not terribly popular with a lot of the current sort of politics and community in the US, but take something, Facebook would be an example. One that always came to my mind was Second Life, which was a virtual reality in which you can live and meet people and do things like dance with them and stuff like that. The natural thing in my mind was for Second Life to have been a cooperative, for it to be owned and controlled by the people who are using it and have the investment in it. Well, I think it basically failed. I haven't heard much about it in years, but I am hoping that a greater openness to new social forms mediated by computer networking will yet make the world a more livable place. Thank you very much. Better have a Coke before I forget what I was saying.
I will let him have his Coke, and as I mentioned, Whit and I go back many years, he only drinks Mexican Coca-Cola because it is the original formulation and comes in special glass bottles. So our refrigerator at Alma's in California is full of very strange antique glass bottles. But with that, now that I've teased Whit, there it is, yes. So
it's not the glass bottles are important, it's being made with cane sugar rather than beet sugar.
Right. So you can imagine the enjoyment of being able to work with a technology philosopher every day for 15 years. So it's been my pleasure over the decades.
15, and we've known each other for 25. I worked for you 24 years ago.
I didn't give you that raise, did I? So what I would like to do is, I'd like to take questions, and I am wearing the translation earphones, so feel free to make questions in Russian. I will relay them to Whit, and then he will be happy to answer your questions. And feel free. So if there are any questions with that, no questions. Whit has answered the meaning of life and meaning of cryptography. So.
Well, I'm glad not to have questions because I never know the answers. So.
All right, exactly. Well, what I'd like to suggest is, if you ponder this talk and you conceive of questions which to some degree are existential or philosophical in nature, please feel free to email Whit or me. I'm happy to forward email to Whit, considering he sits across the hall about 2 meters away. And
at least 4 meters.
We'll be happy to answer anything that you've got. If there are no questions, we're done. Thank you.
Thank you all very much.